Every program needs memory. You create an object, it lands on the heap, and your code uses it. But here's the question almost nobody asks out loud. Who cleans it up when you are done? In languages like C, that is your problem entirely. In almost every modern language, a garbage collector does it for you. But automatic does not mean free. GC pauses, memory bloat, and allocation storms are real production problems that cause latency spikes, query timeouts, and outages. In this video, we are going to pull apart exactly what happens during garbage collection, step by step, from the heap layout to the mark phase, the sweep, generational collection, and the algorithms powering Go, the JVM V8, and Python. By the end, you will know how to reason about GC behavior and what to actually do when it starts hurting your application. So what is garbage collection and why does it exist? When you allocate memory in C or C++, you call malloc and you are responsible for calling free. Forget to free and you have a memory leak that grows until your process runs out of address space. Free too early and you have a dangling pointer that crashes or corrupts your process silently. Both are catastrophic and both are extremely common, even for experienced engineers. Modern runtimes solve this with automatic memory management. There are three main strategies in use today. Manual management, where you own every allocation. Reference counting, used by Python and Swift, where objects track how many references point to them and free themselves when the count hits 0. And tracing garbage collection, used by Java, Go, and JavaScript, where the runtime periodically finds all live objects and reclaims everything else. Each approach has real trade-offs in throughput, latency, and implementation complexity. Reference counting is simple but stumbles on circular references and adds overhead to every pointer right. Tracing GC avoids those issues but introduces periodic pauses that can be hard to predict. Tracing GC is what most developers mean when they say garbage collector, and it is what we are focused on for the rest of this video. Before a GC can collect anything, it needs to understand where objects live. Every runtime that manages memory has a heap. This is a region of memory separate from the stack, where objects with dynamic or unknown lifetimes are placed. When you write new hash map in Java or make a slice in Go, the runtime requests a block on the heap, records the object type and size, and hands you a reference to it. The stack, by contrast, holds local variables with fixed predictable lifetimes. They disappear automatically when a function returns. The heap has no such structure. Objects pile up. A 140-byte array here, a dead string there, a hash map still in use, a socket nobody closed. Over time, the heap fills with a mix of live objects and garbage. The GC's job is to tell them apart and reclaim the dead ones before the process runs out of memory. First phase of tracing garbage collection is the mark phase. The collector starts from a set of known live references called GC roots. Roots are references the runtime can prove are reachable right now. Local variables on active stack frames, static fields on classes, references held by native code through JNI, and active threads themselves. From every root, the GC follows every reference it finds transitively, building a complete graph of everything reachable from anywhere in the program. Any object in this graph is marked as live. If object or references object B and it is reachable, then B is reachable too, even if nothing else points to B directly. Anything the traversal never touches is unreachable. It is garbage by definition. This is a key insight. The GC does not track what you freed, it tracks what is still reachable. Everything else is considered dead. The mark phase is the most expensive part of collection because it must visit every single live object in the heap, and a large live set means a long mark phase. Once marking is complete, the collector knows exactly which objects are alive and which are garbage. The sweep phase reclaims the dead ones. In the simplest approach, mark sweep, the collector scans through the heap and frees every block that was not marked live. Fast to implement, but it leaves holes where dead objects used to be. If those holes are smaller than your next allocation, you get fragmentation. Memory is technically free but practically unusable. Arc Compact solves this by sliding all live objects together toward one end of the heap, eliminating holes and leaving a clean contiguous free region at the cost of moving objects and updating every reference to them. Copying collection takes a different approach. It divides the heap into two halves, copies all live objects to the clean half, then discards the entire old half in one operation. Go uses a variant of this for its young generation. Each strategy makes a different trade-off between pause time, throughput, and memory overhead. Here is the most important insight in all of garbage collection. Most objects die very young. String you build to format a log line, a temporary list created inside a loop, a request object that lives for a single HTTP handler. These are created and abandoned within milliseconds. This observation, called the generational hypothesis, is the foundation of generational garbage collection. Instead of scanning the entire heap every collection cycle, the runtime divides memory into generations based on object age. Gen 0, often called Eden, is where new objects are born. It fills up quickly and is collected very frequently, with pauses measured in milliseconds. The vast majority of objects die here, often 98% or more. Objects that survive a minor GC are promoted to Gen 1. Long-lived objects eventually reach Gen 2. the old generation, which is large, collected rarely, and extremely expensive when it does run. Generational GC is why most applications feel responsive most of the time despite constant allocation. Different runtimes implement these ideas in quite different ways. Go uses a tricolor concurrent mark algorithm. It runs the vast majority of marking work concurrently alongside your application code, stopping the world only briefly at the very start and end of the mark phase. Typical pauses are under 1 millisecond. The JVM's G1 collector divides the heap into regions of 1 to 32 megabytes and collects a subset of regions each cycle, letting you configure a soft pause time target. V8, the JavaScript engine powering Node and Chrome, uses its Orinoco collector, chainy copying for minor collection and incremental mark compact for major collection, with work spread across idle time between frames. CPython is the outlier. It uses reference counting as the primary mechanism, immediately freeing objects when the reference count drops to 0, with a separate cycle collector running periodically to clean up circular references that reference counting alone cannot handle. Every garbage collector occasionally needs to stop the world. A stop the world pause means all application threads are halted while the GC works. This is necessary because the GC needs a consistent snapshot of the heap. If your application is mutating object references while the collector is tracing them, it could miss live objects and free memory that is still in use, causing corruption or crashes. During a stop-the-world pause, threads reach what are called safe points, predetermined locations in the compiled code where it is safe to suspend execution. Pause durations range from under 1 millisecond in modern concurrent collectors like Go's GC and ZGC to hundreds of milliseconds in older or poorly configured setups. For web services, these pauses cause latency spikes and missed SLA thresholds. For databases, they cause query timeouts. Reducing stop-the-world time is the central engineering challenge of modern GC design, which is why so much effort goes into concurrent marking, incremental collection, and escape analysis. Understanding GC is useful. Knowing how to respond when it misbehaves in production is better. The most common GC problem is not a bug in the collector, it is application code generating too much garbage too quickly. When a tight loop creates new objects every iteration, Gen0 fills in under 100 milliseconds and minor GC runs almost continuously, stealing CPU from your application. The fix is object pooling or struct reuse. Memory leaks are real in garbage-collected languages too. If you hold objects in a global map or cache without eviction, the GC can never collect them because they are always reachable. Weak references exist precisely for this case. Setting the heap too large creates a different problem. A 32 gigabyte heap means major GC has to scan 32 gigabytes, producing pauses measured in seconds. Right-size your heap. For the JVM, key starting flags are use G1 GC, max GC pause millis for your target, and fixed XMS and XMX values to prevent resize pauses. Always enable GC logging and measure before touching any flag. Garbage collection is one of those topics that feels abstract until the day you hit a production incident caused by GC pause and have to explain to your team why your service stopped responding for 2 seconds. The core ideas are not complicated once you see them clearly. The mark phase traces from roots to find every live object. The sweep phase reclaims everything else. Generational collection exploits the fact that most objects die young, so most pauses are short. Modern concurrent collectors do most of their work without stopping your application at all. The number one thing you can do to help your garbage collector is allocate less garbage in the first place. The second is to measure before you tune anything. Enable GC logging, study your pause frequency and duration, understand which generation is filling up, and only then reach for configuration. GC is automatic, but it is not magic. The more you understand it, the more predictable and fast your systems become. Thanks for watching.